I love this amplifier. Okay, let's get going. What's up everyone, Joey Pickardt, German audio engineer and guitar player, and today we are talking about the mysterious factor 0.707. This factor is used a lot in amp calculations, mainly for power calculations. In tube amplifiers, but also in other amplifiers. It's not depending on the technology, it's always used when we work with frequencies, when we work with sine waves. Okay? This video should be about really where that factor came from and what we are doing with it. I've seen a lot of videos, some explain the mathematical side, some explain not anything but use the factor, and I want to match these two things up for the audio world. So let's get started. The first part is going to be pretty nerdy, so if you not want to watch that, just want to know what we do with the factor, then jump to the time that I'm blending in right now. Okay, for all the others, you can see it. I've brought my old university calculator. So it's getting a bit mathematically, but I hope you will enjoy and understand it. Let's get started. So, at first, we need a graph. Let's take a graph with the X and Y axis. And now we talk about where that factor is used or how we come to the factor. At first we start with the pretty simplest signal we can think of, and this is a stupid DC signal. So it's not really a signal, it's just not altering anything over time, it's just there with a defined value, it's constant. Let's say we have 1 volt of DC signal. Okay, DC is 1 volt. So we want to know how much power this 1 volt DC is putting out or generating or is happening with 1 volt, but for that we need a load. So we need a resistor. Or for US standards, this sign, and we put a voltage on that resistor. And we have that resistor. Let's say the resistor has 1 ohm. Okay? Now there will be flowing current. Hi. And now we don't know the value of the current, but we know when a current is flowing through a defined load, there will be power. The electrons will move around and will heat up this resistor, and we will have energy transformed from electrical energy into heat energy, something like this. So we can work with that, and we can take Ohm's law. So U DC in this case is our current multiplied with our load. But we don't know the current. So let's take the formula and get the current at the front. So we divide both sides with R, and if we do that, no, this stays here, sorry, the wrong one. So we can solve this to I is U divided by R. And now we can put in our values. This is 1 volt divided by 1 ohm, and this will produce 1 amp. Okay? Now we can calculate the power that this signal is causing, or this DC voltage. Power is voltage multiplied with current, and in this case 1 volt multiplied with 1 amp, and this is 1 watt of power. Okay. Now, in mainly every musical instrument or amplifier or tool technology, we don't want to have DC, we want AC. So we're talking about sine waves, or at least periodically signals, and the easiest one is the sine wave. So let me draw a sine wave into this graph. Okay, and now we'll take the color. We have a maximum of a sine wave, we have the middle position, and 1, 2, 3, 4. Okay, 1, 2, 3, 4 here, and we have the end position. There we go. This should be our nice sine wave. Okay, this is one cycle of the endless sine wave, the perfect signal for us to work with. Okay, now the question is, think about this resistor and think about a power amplifier. We know resistances, they are a bit higher in our usage. They are like on a normal speaker 4 or 8 ohm or 16 ohm for guitar speakers mostly. And we want to know how much power is our amp putting out maximum without distortion, for example. Then we don't have a DC signal, we have the sine wave. But what is the value we can calculate with when we don't have a decent constant DC value? That's a problem. We have an alternating value. So at all these times we have different voltages. So when we have different voltages and we think of our formulas here, we always have altering things in our formula, and our result, the power, will also alter over time. That's a problem. At this point we will have 0 watt. If you buy a 100 watt tube amplifier, you are not expecting that you have 0 watt. So why can they put out a value like this? The reason is we need an average. We need a voltage that is representing our sine wave as if it were a DC voltage. The average over the time over this. And this is called the voltage U, or MS, or the root mean square voltage. Okay? Now, how can we get that? We can easily, this is the first step, I calculated later exactly. We can maybe take short parts of this sine wave and where it crosses. So we take on this axis, sorry I forgot to draw it, we have here the time, of course. This is our U, our voltage. And we have here one period or cycle. So this would be our big T for now. Or if we want so, here would be 2 pi. Why 2 pi? Because sinus is related to a circle, and 2 pi's are the complete rounded 360 degrees circle within one turn. And we have here half pi, sorry, German, and here pi half, and here we have pi 3/4. Okay, so this is how you draw it, and it's relating on the circle, so we have that value. But let's go with a big T at the end, and okay. Then we have a minus down here, and now the graph is complete before I draw and tell you something that you can't see. Okay, we are taking slices out of our sine wave. Now let's get here, okay. At first at the half wave, positive half wave, the negative is the same, but in the other direction, in the negative direction, okay. And now I'm taking slices out of here because let's calculate the area. Okay, these are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. How do we call it? This should be the sine. This is the sine rectangles, and we have 19 pieces. And now let's count how much the DC voltage is covering on area in the same time. So we have this one, and this one in the same time more. So our DC rectangle value is 19 because it's covering all the rectangles of the sine wave, plus 1, 2, 3, 4, 5, 6. So we have 25. Okay, what is the ratio between that both? If we take it, 19 divided by 25, we get 0.76. Interesting. I think some of you, sorry, here should be a point. In Germany we take another point here. 0.76. So this is interesting because my video is called "Where do we use the 0.707 for?" or something like that. I don't know now how I call the video, but it's something like this. And we have a value that is pretty near there. Maybe it has something to do with it. Okay, what have we done mathematically here? We have integrated. Not completely exactly, with a very wide step quantization, but we have integrated. We have built an area over a function. So mainly we can say that we have done something like this. We have done we have summed up all the areas, and let's say we have here a delta from this step and this step and this step and also on, always one delta step, delta t in this case. So we have something like delta t somewhere. Then on the t-axis, okay, then we have the u, and this u is depending on t. So we have taken a value from a position of that slice from t. So we have taking a value u from this position, wherever that is. So we have taken u from t multiplied. Because we build an area, we have multiplied this with this. This is 1 square multiplied with 2 squares, so 2 squares is the answer for the first step. Okay, and then we had added up all the squares here. So add up something, we could draw it like plus, 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 or if we don't know how much we are calculating, I haven't tell you how wide the delta is. We could also draw URMS is the sum of u from t multiplied with delta from t from 0, the start,
until this point, which is pi or t divided in half. Let's say that I can get it complete here. Let's say we have taken the other side also. And I draw it here, just in case to not forget it. But I just take the outer lines if this is okay for you. We're saving time here. And we have taken this for the DC value. Then the only difference between this both is that these values are negative and these values are positive, but the areas are the same. So it does not matter if we calculate this one or this one, only for the negative value. And to get the negative values away, there is a trick that I'm showing in a minute. At first, we can say now that we are integrating or summing up our rectangles until t. Okay? Until t. So now we can square the signal. If we square the signal, we will get something like this. I'm just showing it here because it's just temporary for the calculations. Because the values are squared here, the values are maybe higher, but in this case they won't be higher because we have just 1 volt. They are disformed. We have a sine wave that is a bit stretched. And all negative values in here. So if we get this value or this, all negatives will get positive. So this will get up, like in a rectifier of the bridge rectifier of a power supply. Okay? But when we do that, we need later, after summing up, take the square root, because we want to have this square away. After summing up all the things, we just want to have the negative values out of here. Okay? And then when we build or want to know the factor of something, the average of something, we always do something like this plus this plus this plus this plus this divided through the complete count. So we have to divide through the complete count, and the complete count is all the deltas until we reached t. Because we are summing up from 0 till t, we need to divide by t. So in this formula we have to put in divided by t. Okay, this is nearly it, but we have one problem. This is a sum and we are not exactly at the sine wave. So we can do something. We can say that our value of delta t is going to be nearly 0 or absolutely 0. And if we are absolutely 0, we have a completely continuous signal because we have infinite steps. Yeah? And if we do that, we can do a lot of things with that. We can, the root stays, the square root, sorry. The square root stays. The 1 divided by t stays also. But now the delta is 0. Delta t is 0. We can take our sum function and make it into an integral. Okay? Pushing a bit the time because the video is getting longer and longer and I'm not getting to the point where you all are interested in. We can fulfill that. So u squared t, and then we use the differentiate, I think it is called in English, t and not the delta t, because we are integrating. Okay? Now we need to know what is our u from t to calculate it really. And our u from t is a sine wave. And now it's maybe a bit complicated to understand why, but we're putting in our t because we have a u from t, of course, in our argument is the t. And we multiply it with 2 pi and divide it by big T. This is done because we have to make sure the circles of a circle, 2 pi is related to a complete circle, and divided by the big T also, which is also pi if you want to, and put in the value in that ratio. This is for dealing with the right frequencies in this sine wave and dealing with the right output arguments of the sine. And this is a bit complicated because we have a square to square that signal and to integrate that signal. It's not easy. If we have something like sine squared from something, then there is a solution, and it is 1 minus cosinus of that argument divided through 2. And now I have to think hard about if here is a factor inside. Sorry, this one I think I have to look up. Yeah, there's a factor. We have a factor of multiplying with 2 here. So this is 4 in that. Let's put it in the right order. I can get that line out of there, and we can draw our formula that we can solve this stuff with. Integral 0 to t. And then we put in this term for the u squared function. So we have, this should be an x here at the point because I'm using here an x. Of course it's the argument, but if I use here an x, there should be an x. Now we can put it in, and it is 1 minus cosinus of t 4 pi divided by big T, and this all is divided by 2 dt. Okay, now we can do something here, and I see that I have forgotten something in the area above. No, not here, but here. The sine wave is not only this, it's multiplied with u peak. You will understand it when we not have a value that is 1 volt, it's another value. We have to multiply it with that maximum value that our sine wave is reaching the top, because the sine wave is delivering maximum 1 volt if we don't do it. If we don't have that factor here for other voltages than 1, we will get not the exact peak voltage on this point. U peak. Okay? Now let's put it in here. Sorry, I forgot it. We can put it here. U peak. Okay. And get a bit arranged formula. URMS is the root, how long it will get, divided by 2. This is not having any values here that we are integrating, and the u peak is also just a constant value, in our case from 1 volt, so we can get it out of the integral at this point. Let's do it. The u peak is also the u peak is also squared, and this we have to completely square. Of course, we putting it into something that is squared. Okay, so I hope you can understand me. I'm cleaning up the place now. We have U peak squared divided by t, and we can get this one out of there, so 2 times t. And after this, there's the integral happening. And now we have left this part, and it is 1 minus cosinus t multiplied with 4 pi divided with t and dt. Okay? That is as good as it can get. Now we have to deal with it and integrate. So there's a formula how to integrate stuff like that, and it's just a lookup table. It's like I looked up the solution for sine squared before. We could look up the solution to integrate minus cosinus functions. I will tell you now the solution. The solution is if we integrate minus cosinus something, so like this, we will get sinus of cosinus divided by the argument x. Okay? Now let's do it. You are as is. Okay, this factor stays the same. The root stays the square root stays the same, and this integral is not there anymore. U peak squared divided by 2 times t. And now we're doing the one. Integrated constants are multiplied with this argument t. So we have just t. We have t at the point 0 and at the point t. We have to put it both in here in the next step. And then minus this term integrated, so we know it here. So it's not minus anymore. Sine from t 4 pi divided by t. And then divided through that argument. We can put it down here and put the big term down, or we can exchange it right now, and then we get something like this, divided by 4 pi. Okay. Oh, I forgot, from 0 till t. Let's fulfill the points. Always u peak squared times t. And we have t at the point 0, which is 0. You can see it here. The sine wave at the point is also 0. And t at the point t. So big T. So it is big T. Important is we take the upper value and subtract the lower value from it. So I have to make sure that we have the big T here multiplied with 0. Okay, this term is going to be 0. We know it. Okay, here has to be a body like this one. And we have plus this part, so we take the first one, sine of big T, 4 pi divided by t, multiplied with t divided by 4 pi, and subtract the lower value, 0, t, is sine of 0 4 pi divided by t multiplied with big T 4 pi. Okay, this is easy. I'm using colors to get a bit overview into that. This term is going to be something now, and this term is going to be something now. T and T we can get out of here, so it is just 4 pi. 4 pi, we can look over here. 2 pi is the point where the cycle is completed and the new cycle started. If we take another sine wave and go to 4 pi, we will end up at 0 again. So this part is completely 0. Here we have 0 in our argument. 0, the whole argument is 0, and the sine wave at 0 at this point is also 0. So now we can clean up a lot. Okay, at first the completely part inside of here is 0. Is it really so? Then I've done something wrong. Then we have to leave this one. So what have I done wrong? Ah, here's the problem. It's minus and it's not multiplied. So this term is not 0, this term is t. Okay, so what's left is u peak squared divided by 2t multiplied with t square root. Okay, we can get that stuff out of here. What's left? U peak squared divided by 2. And now we take the square root out of there and we are left with U peak divided by square root of 2. And that's the interesting point. Now let's look what 1 divided by square root of 2 multiplied with any U peak voltage that we deal with is. Let's say we have 1 volt. We have 1 divided by square root of 2. And this is this amazing factor 0.707 and some rest left. So we have 0.707 multiplied with our U peak. And that's the reason why we use the 0.707 for calculating in amplifiers. We want to have an representative DC voltage to calculate with, which is representing the sine wave average voltage. If we can call it like this. I know some people out there are going to hate me about that, but I don't know how to better explain it in English. This is the reason. We are using 0.707, or it's concrete 1 divided by root of 2 multiplied with the peak voltage to get an average voltage, and now we can calculate like it is an DC voltage without dealing with any of that stuff. We can go up here and we can take our URMS value, which is in this case, let's put it here as solution. URMS is U peak. U peak is 1 volt multiplied with 1 divided by square root of 2, and it is 0.707 volts. Okay, and now we can take this voltage and put it into our formula, and we will get the concrete power output of our amplifiers like we want to know it. And if we do that, our 100 watt tube amplifier will produce 100 watt output power if the manufacturer has done the right thing and written the right thing. Okay, I hope you could understand my totally mess on one page, and my math was not too complicated, and sorry for the 2 mistakes, but this is the reason for the factor. So hopefully I have made a few people happy to understand now why this factor is used, and maybe I'm putting a short video on the end of that video how we measure a real voltage on an output of an amplifier and calculate how much output power that is. Okay, let's get our hands dirty with this beast of an amplifier, the Mesa Boogie dual rectifier in the 2-channel version. It has 4 6L6 output power tubes. They should deliver around 100 watt, but let's find out with our new formula that we have learned and with that mysterious factor 0.707. I have a dummy load here with 15 ohms. It can handle 150 watts, so it should work with that power amp, and my oscilloscope. The oscilloscope is connected at the first channel with the slave out of the amplifier, just to have a look at the signal and know that the signal is coming into the amplifier, not for measurements. And the second channel is connected directly to the dummy load. Okay, the signal is coming out of my computer, out of the audio interface, into the effect return of the amp. So the complete preamp is not included because we don't want to have any kind of distortion or noise shaping. We just want to have the clear sine wave, and the only thing that is working is our volume knob here. Okay, I think we can start. Let's power on the amp and let's get the volume up. And here you can see the sine wave. Okay, channel 1 is yellow. This is 10 volts per division. I have the slave output totally turned up, so now I turn it down. We have seen the sine wave, we know it is there, and now we are concentrating on the blue channel, and we can see, make it a bit better here, there is a sine wave that is on this resistor right now, and here is the division, volts per division, 5 volts per division, so each of that line is representing, or the step is representing 5 volts. So if we take this, we have a peak to peak of 20 volts, and we can see it down here, nearly 20 volts, pushing a bit higher though, there we go. Okay, so now we can push up our voltage, and we have a nice sine wave, 40 volts, turning down the divisions. Okay, now we have 60 volts peak to peak, 80, and there's nothing. No top, no problem, it's a clear sine wave. Okay, I'm going down one step further in the divisions, and now we are looking for something that is distorting our sine wave, normally at the top or the bottom of the peak, because there is the point where the power amplifier is delivering no more voltage, so the power amplifier is getting into saturation because the power supply is not delivering more voltage. Okay, let's push that, push, and there is our top. Here we see it, and there is it down. And how much voltage do we have? 100, peak to peak. Okay, let's get down and don't do it too long because the resistor is getting warm. 100. I'm doing it again so you can have a closer look on what is happening here. We rise, and on that point, this is the point what we are looking at. This is the maximum. Here is the distortion beginning. This is a nice sine wave. It's a bit disformed but not totally, and this is a flat top and this is a flat bottom. That would sound in an audio amplifier not nice. In a guitar amplifier this is maybe wanted, but let's stay here. We are around, okay, let's be nice. Let's say it's 50 volts peak or 100 volts peak to peak that this amp can push out because it's an old amplifier. And turn it down. Thank you very much for delivering us this nice sine wave. And now we have to calculate. I'm using the formula that we have drawn together. At first I'm using the factor, so I just put it on the calculator and show it to you. You can see the formula in here. I'm using 1 divided by square root of 2 multiplied with our U peak, which is 50 volts. And I'm taking the square because our power calculation is U squared divided by R. So we divide it through 15 ohms. And this is our result. 83.3 watts output power. I have the U peak, our factor, and divided by the resistance that is measured on, and we have nice output power, not the expected. Should be maybe higher, but as I said, it's a musical instrument, it's an amplifier for guitars, so maybe they have planned to work with that, or maybe, I don't know, the caps in here are maybe 30 years old, so I don't know, maybe if it's brand new it is delivering more output power. This could also be. So we can be sure that this calculation is correctly, that this power is delivered, but next time maybe we can expect a bit higher value from a 100 watt amp, but it's not bad. Okay, now you know how to calculate it, and I hope you could learn something, or you could at least have an interesting time with me, or at least laugh at something that I have done here. I don't know. Please like me or not, it's a free land. Subscribe and have a nice day. Till next time.